All right, we are starting with simple harmonic motion, and we are going to introduce, I'm going to introduce this with a mass spring system. Okay, and so we're going to attach a mass to a wall. And this mass is, well, it's a crate, and it's on wheels. Okay, so there's no friction on the bottom. And this crate has a, everything is at rest here. This is a spring, and an ideal spring. You can compress an ideal spring and stretch an ideal spring in either direction, and you'll get similar effects that you'll have if you compress a spring. You will get a force that is pushing against the direction of compression. Okay, and if you stretch a spring, you'll get a force that is opposite the direction of extension. Right. So it's Hooke's law was the force of a spring equals negative kx, where spring is where k is the spring constant, right? So, so that's where this cart is. However, this cart is on an unstretched and uncompressed spring. It's just sitting there with the spring. We can move the cart, and we can stretch it out to here, and we would have our cart that would have this extension out to here, and it would pull back. And so at this point right here, you know, the force body diagram of this thing, we would have a, you know, we've got normal, we've got mg, and then we would have this force of the spring that's pulling us back. Okay, we could also go the other way, although I wouldn't be able to compress it that far. If I were to go this way, we could compress another distance here and make our cart there, and we would have the same thing. We would have our normal gravity, and we would have the force of our spring going the other direction. All right. So at any particular time, if we are not at the uncompressed or unstretched position, if we have some sort of tension in the spring, then the only force that's acting on this cart is the spring. So the sum of the forces we know is equal to our mass times acceleration. This equals, it's going to equal negative kx. Yeah? Good so far? Okay, we can explore this a little bit. Our acceleration would then be equal to our spring constant divided by our mass times our distance. You follow that? Yeah? How is acceleration related to distance or to displacement? It's the second derivative, right? It's the second time derivative of displacement. So we can rewrite our acceleration here as d squared x dt squared, right? Equals negative k over m x. And what we have here is now a differential equation that is really, really hard to solve. So we're screwed. That's the end of the lecture. No. Thank you very much. Okay. Now, if we are to graph this, it is actually possible to graph this. And what happens is we get a graph that looks like this. That if this is our displacement, and this is our time, okay, at time 0, if we stretch this thing out and give it a positive displacement, okay, as far as it'll go, okay, we start at time 0, okay, and then we let go. And what happens is it starts to accelerate back towards the other direction until it gets to here. But once it's at its uncompressed state, because this would be where x is 0, this is where we initially had it, its uncompressed, unstretched place. Okay, it's moving. It's not going to stop there. It's actually going to compress into the spring again, and so it'll continue down. So if this right here is positive x naught, then it will continue down until we get to a negative x naught, and it will go all the way into the spring the same distance that that we had it extended it. And the same process will continue on and on. And if we have a frictionless surface, and if all of our forces are conservative, we have this pattern. Okay, what does this graph look like to you? This is a cosine. All right, now I prefer to start with cosine. You can start with sine. We'll get to that in a minute, but the math will show why I like cosine better. Okay, so this would match. Okay, we'll get some stuff out of the way here. This matches x equals cosine t, right? It has that shape. But let's really put it together. Our x of t is going to equal, and we're coming down here, and this, we call this right here, this maximum distance from our 0 point is, for something that moves like this. Okay, so this height right here, or actually any distance, this maximum distance from our 0 point is called an amplitude, and we're going to give it the variable a in our equation. It just stands for our maximum displacement. Okay, and there's going to be a cosine. All right, and we know that this is a variable based on t, but we have other factors at play, because we could have how far shifted over it is. So this wouldn't have to be right here spot on the maximum point of the cosine, right? We could have it, we could have it start here, and then there would be this shifted value to our graph. And so this is called the phase angle. We're going to call it here, we're going to call it theta naught. Oops. There, we'll call it theta naught. Okay, and do you guys remember what this one is? Sort of. Okay. It helps us find the period. We're going to call it omega. Yes, that omega. All right. No, not that omega. Okay. Not the one you're talking about. Okay. So, here's our position function. Okay, but we started this whole thing with acceleration, right? So let's find our acceleration given this position function. All right, so v of t is going to equal negative, because the cosine is going to be, right, derivative of cosine is negative sine, a omega sine omega t plus theta naught. Yeah? Okay, so that's going to be the velocity of our particle at any particular time when we're oscillating like this. To find the acceleration, okay, we do it again. Okay, so derivative of sine is going to be cosine, but if we have the negative up front, it doesn't change the sign, so it's still going to be negative. That's still going to be a. That a doesn't change. But now we have an omega squared. Right? This omega, we take the derivative of the inside. Yeah? Okay, then cosine omega t plus theta naught. But look at this. A cosine omega t theta naught is the same as A cosine omega t plus theta naught. What? Oh, my voice is yes, my voice is not in the best shape. Okay, so when we reset this as our acceleration with respect to time equals right? You guys following that? Well, that was this here, right? Okay, hopefully you already have this on your notes, so you don't need to see it on mine. Okay. All right. That this A cosine omega t plus delta is what x of t is. So A of t is equal to right? Oh. Okay, and so what happens is, look at that. Our negative k over m and negative omega squared fit the same place. And so our angular in radians, this has to be done in radians, by the way. Just saying, you've got to do, this calculation only works in radians, not regular degrees, only radians. Okay, so the frequency, the angular frequency of our oscillation is equal to the square root of our spring constant divided by our mass, the mass of the object. Okay, so this is this right here, this dx squared over dt squared times some constant times the x. This is our signifying equation for a simple harmonic motion, this one down here. Okay, and it winds up being that this constant that's in front of our x, okay, is our angular frequency squared. You follow me there? So this is how many radians, this is our radians per second, right? Yes. This is how many radians per second we travel. So, how many radians are there in one full cycle of a circle? 2 pi. So, our frequency of any our frequency of rotation, how often we go around, our cycles per second, okay, is equal to 2 pi k over m. Let me make sure I've nailed that. No, I lied. It's the other way. No. Okay. Sorry. Omega over 2 pi it's over 2 pi. Okay. So if we divide our number of radians by 2 pi, that's going to give us how many cycles we have. That's okay. Okay, revolutions, right? Cycles, revolutions, same thing. So our frequency becomes 1 over 2 pi root k over m, or our period. Okay, we call it big T. This is period. Okay, or in other words, the time it takes to go through a complete cycle is then 2 pi m over k. Okay, and this is our, no, this is the frequency of our oscillation here. All right. Yeah. If this is cycles per second, cycles per second is frequency, guys. Okay, so period would be the time for one cycle, which is the reciprocal, so we flip it over one. Okay, so that's the basis behind simple harmonic motion. Recognize that if you do this, if you have this acceleration is related to x, particularly with the negative here, this happens with the restoring force. This happens when your displacement causes a force that would return the object to its original position. It's the only time it happens. We have two forces that cause this. One of them is a spring. The other one is gravity. We will get to gravity in the next lecture. Okay, but for now, we want to talk about our energy considerations with simple harmonic motion. Okay. So, if you remember back over here, we have our cart that's oscillating back and forth between, let's call it here, because I want to make our distances at least look equal. Okay, so we know that considerations, yes. Okay, so what's going to be the energy of this system? Well, our energy, the energy at any given time is the total potential plus the total kinetic, right? So we have the potential energy that's stored in the spring, and we have the kinetic energy of the object that's oscillating. This is going to be the energy of the system. Okay, and we know that once we let this thing go, that the maximum kinetic energy, the maximum energy it could have at any time is equal to the maximum potential. Yeah? Okay. So, and the energy of a spring, or the stored energy of a spring, is equal to one half kx squared. But in our example here, our x is really the amplitude of our oscillation. So it's really going to be 1/2 Ka squared, where it's the maximum, the amplitude of our swing here. Well, if our cart is in the middle of our swing here, if our cart is in the middle, what's our potential? It's zero, because we have an uncompressed, unstretched spring, right? We're not affecting the spring at all, and so all of our energy would then be kinetic, right? So all of our energy would equal K, but the value of it would still equal the 1/2 Ka squared. It would still equal the value of our maximum potential. All right, now what was, and here's the beauty of this. This is so awesome. Total energy at any particular point on here, however, is right? It's our 1/2 Ka squared plus 1/2 mv squared. Did we find out what the velocity was for our spring? Did we figure this one out? Here's the velocity for our oscillator, right? So we've got two things. Hold on. Oh, I'm sorry, hold on. I'm going to keep that as an X, not an A. Sorry, guys. Okay, so our energy as a function of our position is going to equal 1/2 K times, okay, what was our X of T? Well, our X of T is A cosine omega T squared, right? If this is our position, if X equals A cosine omega T. And our velocity gives us right. Yes. Well, for simplicity, we'll just say we started in phase. Oh, yeah. Squared. Okay, so let's expand these. So we're going to get, you guys might see what's going to happen right here. You guys might see what's going on. All right. Okay, but what was omega squared? Omega squared is K over M, right? So yeah, as Schmidt said over there, the M's cancel out. So what are we left with? If we factor out okay, and this of course is one of the most beautiful trig identities. Whenever you see this, you rejoice because it saves you a heck of a lot of work. Okay, cosine squared plus sine squared, of course, equals 1. No. All right, that cancels to 1, and so the total energy is equal to K squared at any particular time throughout. So, what does this imply about a simple harmonic oscillator? Energy is conserved. When you have a simple harmonic oscillator, energy is always conserved. That's your lecture.